All right, let's see here. Houston, how are you doing? Gonna have to start typing here in a minute, Houston. We can't keep doing this all day. Such a funny kitty. All right. Well, I guess I might as well get cracking here. Let's see. What do I have planned for today? I've got basically three main things that I want to accomplish today. So, first one is that there's a few kind of straggler bugs and issues that have to be worked out. So I think we'll take a look at that first. Second, let me see here. Second, the card that we're using, it has two Ethernet ports on it, two SFPs, but the way the code is written right now, only one of those ports is actually usable, basically. So what I need to do... Oops, all right. See you later, Houston. Let me turn off the cat cam. Okay, there we go. All right. We'll probably see Houston again later. So what I need to do is set things up such that both of those ports can be used. And then the third thing I want to do is sort of do some cleanup on both the driver and the verification framework, the Python, to make things a little bit easier to use. As of right now, the Python code that I'm using for testing is very, very simple, and while it works for some like sanity check type testing, it's not ideal if you want to, say, run a few thousand packets through the design. So let's go ahead and get cracking here. Oh, one other thing I wanted to mention is that I had kind of a similar epiphany, I guess, while I was building Corundum in the first place. But this code that I put together here over these live streams, I think is useful, for educational purposes as its own project. So I'm actually going to release this as sort of a separate design. I'm going to call this Corundum Proto, and the idea is that it's really for educational purposes. It's very simplified, and hopefully that makes it easier to follow and easier to understand. Okay. Let's see here. So I've gone ahead and moved everything into a separate Corundum Proto folder, although I may actually shorten that to C Proto instead of Corundum Proto, but we'll roll with that for the time being. And I've gone ahead and renamed everything, and I've also changed to the PCI Express device ID, because the idea here is it's going to have its own HDL and its own device driver. So as we add features and capabilities to the full version of Corundum, we'll still have the simplified driver that you can look at for educational purposes, basically. At some point, I probably need to go through and add some additional comments so the code is a little bit easier to follow. I mean, right now it's not too bad, but it would make sense at least to annotate the HDL in a few places. All right, so let me think here. First thing to do is to recap where we ended up last time. I think I've also done a little bit of reorganizing in the driver as well. So I think I had the net device file, and I have split this out into RX and TX code, but this was basically just a copy and paste of the receive and transmit related code. So, no new code here, it's just some reorganization. All right, so let's take a look at where we stand here in terms of the actual hardware. So I have the current design built and loaded onto the card, and here is the D message output. And yeah, we have this here, and we have the this is TCP dump running on my workstation machine over here. Okay, so I'm going to go ahead and we'll load the driver, and we'll see what happens. Right, load the driver. and we're getting some traffic flowing through here. Where did my pinger go? All right, so let's pull up ping, just a regular ping. And I need to add an address. Boom, there's an address. Okay. It wasn't working for a second here. Now it's working, so that's good. Right. So we're pinging. That's great. So the first issue that we have is that if I run like a flood ping, it stops quite quickly. So if we look at the driver output here, we're just seeing interrupt, 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 interrupt. So something, so the card is still generating interrupts, but the driver is not handling anything. So that's a problem. And let's see if we can figure out what happened here. So if we look at what's coming in on the RX side, right? We've got packet for TX, interrupt, okay, process RX. It writes a descriptor. Oh, this is for a transmit packet. Okay. Process RX descriptor. So we're working our way through, right? 248, 249, 250, 251, 252, 253, 254, 255. Right? So if we reach the end of the RX queue, at this point we should be wrapping around back to the beginning of the RX queue. But we don't see any more process RX completion messages at this point. So whatever's going on, it has to do with, as it appears, it has something to do with the RX completions. So either they're not getting written to the right location, or maybe the phase tag values are being written incorrectly. So let's take a look at the simulation, and we'll see if we can determine what broke, basically. Because if you can replicate a problem in simulation, that's always better than, you know, trying to use the ILA and poking around in the dark in the hardware. Yeah, the ILA, it's a really nice tool, but if you don't know where to look, it's it can be a problem. Actually, hang on a second. I'm gonna do make clean, make. Okay, to rebuild this and get the simulation waveform so we can take a look at what's going on here. Let me also take a look at the Python code for the simulation and see what's going on here. I think, did I set this up to send multiple packets? Yeah, okay. So I did set this up to send a handful of packets, and we will see what this looks like. Yeah, annoyingly, because Verilator has to recompile everything, it takes a minute to do that. I guess while that's running, I can start putting together a top-level simulation for this. So this one is nice in that it's for basically the core of the board, but the idea is that we want to be able to do a test of the design and isolation of the board. So if I go into TB, all right, so I'm going to copy that, put boards, right, yeah, back here, okay. What did I call that? Oh. Okay, cool. So we can do that. And then I'll need to update that for the board here. Or rather, to remove the board specific stuff. Alright, so this is still not done building yet, so we'll keep working on this until that's done. Okay, so we're looking at all this Mac related stuff here. So in this case, we need to create a bunch of AXI stream interfaces. And that replaces all of this. Okay, so we've got that. All of this I think is fine. GPIO, that goes away. And then the clock. All right, let me double check this here. Okay, so I have PCIe clock and PCIe reset. Okay, so that also goes away. Great. All right, and then for this, I just have ports, RQ, sequence number, and the bar aperture. Okay. Okay, that looks good. Oh, and this is not that. This would be. There we go. And I think all of this, all the PCIe stuff is the same. That goes away. Okay, let me double check on this here. So I need, yeah, I need these guys. So put the ports on the top, and then we have the sequence number width and the bar aperture there. Actually, I guess the sequence number width is computed here, so I can convert to that. Okay, great. Oh, and again, this is that's going to be set up like that. Okay, cool. And this one, I think all of this should be pretty straightforward. Again, it's just a matter of fixing the. Put the Mac models in here. Oh, all right. This one did finish running. Let's take a look at this in the in Surfer. I've been using the new Surfer waveform viewer, which it has some significant problems, but it's got a few warts in there. Let me see. Open that in the default application. All right, so I got a question. Why did I choose CocoaTV instead of UVM when I started Corundum initially? Well, basically, let me think of the. Well, yeah, basically it goes back to when I started working on all this stuff. I've been using primarily open source simulation tools, and the open source tools have only supported UVM very, very recently. So I think like Icarus Verilog still doesn't support it. I think Verilator got support for UVM on some level. I don't know exactly what it can do, but this was like maybe a month or two ago, something like that. So it just has not been an option until very recently, at least in terms of what I've been doing. And I haven't really had access to the commercial tools. I've used obviously ISC and Vivato and whatnot, but in order to make stuff, say more deployable, like in terms of being able to take advantage of GitHub actions and such, it's easier to use open source tools. So CocoaTV has ended up being a very nice setup for this. And once you get it working, then you might as well just keep running with it. Yeah, because I've got a whole bunch of CocoaTV simulation code behind the PCI Express stuff, behind the Ethernet stuff, and to port all of that over to UVM, that would take a lot of time and effort. So yeah, I'm just going to keep rolling with it, at least for the time being, until there's a compelling reason to switch. All right, so let's go take a look at the completion write code and see if there's something clear for what's going on with this thing. All right, so we've got, what did the code do originally? Right, I think we sent one packet, we received one packet, and then I sent 4 packets. So I need to look over here and see if there's something clear going on. So the producer pointer, that's incrementing, right? It goes 2, 3, 4, 5. What should be happening is that this should be wrapping around, right? So this, I should have set this up. Well, I guess the value should be here, right? The size, yeah, RxDQ size is at 2, so that should mean, well, and also the TXDQ size is 2, so that means there should be 4 elements because it's 2 to the power of whatever the signal is. So 2 means 2 bits wide, so in this case, it should be written back at address 0, and it should get the other phase tag value. We're not seeing the phase tag, well, okay, so one thing is we're seeing the phase tag reg set to 1. So that is suspicious. Let me also see if I can get the completion record out of here. Let's look at the HDL for a minute. So when we factor in the, all right, so this is the address. The destination address, does that wrap correctly? This is in write descriptor request, and we're looking at the request destination address. Zoom in a little bit here. Okay, so this seems to be wrapping around, right? So we've got 3010, 3020, 3030, and then it goes back to 3000. Okay, so this is wrapping correctly. But this is suspicious. When this thing generates the completion, let me remind myself how this works. Okay, CPL combined, that is going to be, okay, so that's going to be the data, and then this gets combined with the phase tag here and passed out to the read response data. Okay, so that goes out through, yeah, the DMA engine will read that. So I need to look in the DMA RAM read, and I could look at the read response data. Okay, there it is. Here's the read response data, and what do we got? This 8 right here is going to be the phase tag, and that's set the whole way through. So it looks like the phase tag is being generated incorrectly. So is this just an off by 1 error? Yeah, I think I specified these wrong. So I have TXCQ size plus 1. I think I need to get rid of these plus 1s. All right, let's rerun that, and we'll see what that does. Yeah, that's probably the issue, because if TXCQ size is 2, right, then we should be looking at bit 2 to generate the phase tag, because bit 0 and bit 1, those are parts of the pointers. The bit 2 would be used to determine the phase tag. So yeah, you don't want the plus 1. All right, we'll rebuild this, we'll test it, and we'll see what happens. All right, so you're thinking of a comment saying the audio might be breaking up. I'm not sure if I can do anything about that, unfortunately. Now this is reporting dropped frames. Is there anything I can do about that? Wasn't doing that the last time. But what changed? Let me check on a couple of things here. Well, it's not reporting any drop frames at the moment, so I don't know. Downside of trying to stream off of the same machine that's potentially running Vivado and other stuff is that occasionally you might run into issues with, you know, CPU memory contention type stuff. So hopefully this won't be an issue, but I will try to keep an eye on that then. All right, so we'll give that a minute to finish. In the meantime, I'm going to take another look at this code over here. First thing is to get this to build correctly. Okay, I need to fix this as well. To do that. Okay, and then yeah, I guess this is just going to be .f. Yeah, okay, then that can go away. All right. And then I think I need to specify at least some of these parameters here. I guess mainly just ports and bar aperture. I'll get rid of everything else for now. Or I guess maybe I don't even need to bother with that. All right, I'll just comment this out for now. Okay, and same thing here. This needs to go over here. Oh, crap. Okay, so that ran. Let me take a look at Surfer here. We'll reload that. Ah, okay, that seemed to have done something. So we can see now that the phase tag reg is getting cleared. So this descriptor, when it gets written, presumably will have the correct phase tag value. Yeah, okay, so we've got the request dest address. Yeah, so this one, 3020, that's fine. 3030, that's fine. 3000, I'm guessing this one ends up getting written around here somewhere, because when this read hits, that bit is cleared to a 0. Okay. Hopefully that solves that problem. All right. So now we got to go locate my Vivado build window here. I think, yes, that's Vivado. So I'm going to go ahead and fire off a make, and we'll let that build. When that's built, we'll try it and we'll see what it does. In the meantime, I'm going to continue chipping away at this. Yeah, okay. It sounds like the audio is working a little bit better here. Yeah, OBS is not reporting any more drop frames. So I don't know exactly what happened, but it's working a little bit better now. So yeah, it's like there's quite a few things that could affect that, right? One of them is CPU utilization, memory utilization type stuff locally. But it's also potentially possible that there's some sort of like network bandwidth problem. I don't know. Unfortunately, the connection I have here is one of the asymmetric ones, and the upstream bandwidth is only like 10 megabits a second, something like that. But you would think, in the U.S. being, you know, one of the founders of the internet, effectively, right? Would have better internet connection capability. But no, there's a lot of areas here where you have just absolutely terrible options for internet. So we're paying a lot of money for terrible cable connection. What are you gonna do? I guess you can move, but yeah. Okay. So where was I here? I guess what I need to do now is open up another terminal window and see if we can run this. Up a lot here. Okay. Oh. Oh, I need to rename these as well. And I don't need the base R file. Well, I'll leave it there for now. Okay, rename. Okay, renamed. Oops. Okay. So we'll try doing a build on that. Yeah, so ultimately what I want to do is reorganize all of this stuff so we have a nicer way of like explicitly sending packets and such. Let me see, what is the next thing that I need to do here? Oh, right, I need to go and put the AXI stream interfaces in here properly, because this one is complaining about AXI stream stuff not being declared. So, great. I will go ahead and copy that actually out of, I think, here. Oh, actually, not here. I want the code here. how is this set up? Right, so we have SFPTX, SFPRX, TX completion. Okay, so you'll start with these. Gotta go all the way down here. Okay. So this is going to be Mac axis. All right. Okay, that looks good. And then these twos that can be replaced with ports. And then I also need to define the clock and reset connections for these. Okay, clock and reset. Be the Mac TX clock, and same thing for the resets, or for the RX. Oh, and I need to define the Mac data width as well. I'll put that up here. And I'm also going to go ahead and make these a little bit easier. It's nice doing things on one line, but sometimes it's actually a little bit more sensible to put everything on one line like this. Okay, there's that. And then I got to do that one more time here. Okay. So Verilator seems to be happy with that. Now it's a matter of what needs to be adjusted over here. Yeah, because this is gearing up towards being able to actually push this up to the GitHub repository. All right, so that failed, but that's fine. All right, so I need to go ahead and create a another Python script here. So this is going to be used for the actual device driver simulation model code. Let's check on Vivado. It's moving on to the build now. Finished the synthesis, going on to the build. Okay. All right. So what do we need to do here? Actually, let me see if I can get this code running first. And then it's just a matter of kind of reorganizing stuff. All right. Let me see. Why do I still have this line around here? That's definitely not required. I'm going to keep this stuff because I'm just going to rename the objects in a bit. What I do need is the Mac model instance. Let me see if I have, if I can pull that from the legacy version of Corundum here. Where would that be? I guess I can go over here. All right, so I need to go over to CocoTBX Ethernet, and I need that. The Mac model. Okay, everything else I think is fine. And then for the Ethernet Mac, let me see exactly what needs to be done here. So all of the, so this can go away. I don't need the 125 megahertz clock. I don't have a reference clock. I'm just going to comment all this out for now, and then I'll clean it up. All right, so we don't need that. There is no 125 megahertz clock. There's just a PCIe. Well, all right. We do have the Mac clocks though, so all right, I'll leave that alone for the moment. This is configuring the bar. That's fine. Sorry. All right. So Ethernet. All right. I don't want to comment this. Self.port Mac. So we're going to create one Mac for each port. That's pretty straightforward, I think. Let me see here. Okay, so we can look at the width of these things. Well, I'm going to leave this alone for now here. So I can type. All right, so the clock period, I'm going to call this 3.2. I don't think that's quite right, but we'll roll with that for now. Speed is going to be 10 gigabits per second. And now I need to loop over the ports. So this is going to be actually, I guess what I want to do is, I don't have a single hierarchy object that I'm working with here, so I'm going to do 4K in range. And then this is going to be length of that. Okay. So I need to start all the clocks for one. And this is going to be Mac TX clock, and this is going to be F clock period. Yep, okay. We're going to do this again for the ARX clock. And I can also do something similar for the resets. Set that to 0, and same thing for RX. And then I'm create the max. Right, so this is going to be, so this thing is it's a model of the Ethernet Mac. Got a question here. Is there a monthly meeting video explaining the architectural details of the DMA engine in Corundum? Well, so there is a monthly meeting where I kind of present what's new. Nothing has really changed in the DMA engine in a long time, so it's not really something I talk about regularly. If I make changes to it, then I'll probably talk about it. If somebody wants to hear about a particular component, I guess I might be able to go into some more details. I would recommend, ask on Zulip, and we'll see. Maybe I can plot some stuff in. Oh, I almost forgot. These need to be indexed. Otherwise, it's not going to work very well. All right, TX clock. In this case, I now need to connect all the signal to the Mac. So we got the TX clock, we got the TX reset, right? And I'm also going to need the same thing for RX, one step at a time. So RX clock and reset, and then I need to create the TX plus. That's going to be this is from from entity. Okay, and then I need to do this again for RX. At the IOQ setting and the speed setting. Okay, I think that is all of the main stuff that the Mac model requires here. So let me go ahead and see, where was this? Okay, let me see. Oops. I will rerun this. Yeah, so this got through the, let's see, did the setup, the initial creation of the PCIe core model in CocoaDB. But then it failed out with the clock problem. So, okay, it's rebuilding it. We'll check in a minute once this is done building. And let's see what Vivado is up to right now. Okay, it's finished crowding, so we'll have a bit file to test in just a couple of minutes here. Alright, so I think all this is looking pretty good. Okay, oh, well, it's going to be complaining about a bunch of this stuff, so let me think for a moment here. Did I do this correctly? Yeah, that was, did put that, okay. Okay, this is going to be mac.rx.reset set immediate value. Set that to 0. And then I do that again for tx. And then get rid of that. And then I got to do this again here. In this case, I'm going to set the value of these things to 1. And I'll do that one more time. Well, I'll go ahead and clear them out here. It'll be right using the PCIe clock. Okay. All right, and then this can go away as well. Okay. Yeah, so that failed again at the same point here. Well, not at the same point, but that failed in the reset. So it got further this time because it created the Mac TX model, Mac RX model, and it was able to connect to the AXI stream interfaces. So that looks good. Okay. All right, so this got further. This got all the way down to, where is this, line 433? Yeah, okay. So this one, PCIe clock, okay. It's gonna run this time, hopefully. Oh, okay, so it got all the way down to sfp syncs.clear. Okay, I actually don't need to bother with that here because we don't need to wait for the block lock. And then what we're doing here is we're actually interfacing with the Mac model instead of the base R models. So let me go ahead and update this. I'm going to double check exactly what I need to do here. Okay, so I think I'm just calling... Oh wait, no, I'm not doing that. Okay, yeah, so for sending stuff, what I'm going to do is I'm just going to call the, let me see, this is going to be port mac 0.tx.send, no, .rx.send, because we're sending it on the RX side. And I think I can just do that. And then in the TX side, I'm doing port mac 0.tx.receive. Okay. Let's see if that works. Okay. Oh. And then there was another one of these down here. Okay, but that looks like it did actually work. So that's perfect. We did everything correctly here. So we have a bunch of writes to initialize all the registers. Yeah, okay. That looks good. Okay. Great. So this is not really, I've just created the test bench now. The next step is to do some of the reorganization. All right, let me take a look at what Vivado is up to. All right, we have a bit file. Great, so let's go ahead and I'll go ahead and program that, and then we'll go from there. Let me see, where did I put? There's number 1, there's number 2, there's number 3, and I think I have, okay, there we go. All right, it's reprogramming the board now. Once that's done, I can go ahead and reset it. Okay, so that's programmed, so we'll reset it. Well, I was not hoping for that. What happened exactly? This fired an interrupt. Oh. I guess it fired an interrupt before. Yeah, if you don't get all the sequencing right, then you can have weird things happening. So think about that here. I thought I had unloaded the driver. I guess I didn't actually unload the driver. Well, that doesn't help, does it? All right, I'm gonna have to reboot this. Oops. Nope. This is completely hosed. One moment. Let me think here. What's the best way to reboot this thing in this condition? One moment. I'm gonna have to go in via the IPMI controller. Or maybe not. I can't remember the password I have set on this thing, so I got a hard reboot and then reprogram the FPGA again. All right, we'll give that a second to reboot. Okay, so where did that crash exactly? I wasn't expecting the interrupt to take place immediately after registering it. I guess what happened is that the interrupt tried to look up the net device priv, but there was no net device registered, so that was a null pointer dereference. Alright. Well, at least that's an obvious problem. Well, one of the things that I'm going to need to do anyway is to move the interrupt implementation basically into the actual net device handler. So that will at least partially solve this problem, because the idea is that we're not even going to register the interrupt handler until we've already created the net devices. Because once we have multiple ports set up, what we're going to have to do is have a let me think about this for a second. Yeah, we're going to have well, I guess we don't really have, we could put everything on one interrupt, but it's going to make more sense just to have one interrupt per port. I guess what I can do for the time being is add some code here. Is if cdev ndev, then we will just return here. Okay. We'll do that and hope for the best. Go ahead and pull up everything again. We need to increment our crash count. I don't know what the current count is right now, but crashed it again. What are you going to do? Alright, it's not up yet. I don't think anyway. Oops, let me disconnect here. Oh, there we go. It is up. Okay. I also got to figure out why this is not accepting my SSH key. That's quite annoying. Okay. So there we go. And then I need to reprogram this again. Alright, here we go. Yeah, okay. Okay, Vivado taking its time starting up. Yeah, so the nice thing about the design that is in the flash on this card is that the bar configuration is, shall we say, compatible with Corundum. So I don't need to reboot the machine again after programming the FPGA. If the flash was blank, then I would need to do that. And that can actually be a problem on some machines, because if the card doesn't enumerate when you initially boot up the machine, then it doesn't necessarily rescan that slot. These machines happen to be just fine with rescanning the slot, but that's unfortunately not a given. Alright, so let me go ahead and do a hot reset. It looks like that programmed it. Okay, there we go. So we can see the device ID here and the bar. Perfect. Okay. And let me go ahead and I have another. Where was this thing? Okay, there we go. Go ahead and transfer the module over. We'll build it, make sure it looks good. Oh, right. Okay, there we go. We've inserted the module. It seems to be running now. So let me go ahead and see if ping works. Now, where are my notes here? A lot easier to copy and paste some of these commands. So we'll set the IP address. Okay, we have an IP address, and now it should be able to ping. Okay, there we go. Ping is now working. Let me try the flood ping. All right, so it's running, right? It has not crashed this time. So that definitely solved at least one problem. Oops. Leave that going. Let me see what happens if I try something like iperf. Let me think here. So I'm going to do iperf 3-s, and then over here I will do iperf 3-c. Okay, perfect. So I will do that. And we lost the IP again. Okay. Whoa, what happened? SWIOT buffer is full. Uh-oh, what happened this time? Whoa. Pairing RX desk. Okay, this has got to be some kind of a driver bug. This is just continuously looping through the entire RX ring. Oh, wow. Why is that happening? Yeah, this is just, it's just continuously filling the queue. So somehow, I mean, I guess it's not an infinite loop, because at some point it, well, what caused it to fail? Maybe it failed because it couldn't map it. Yeah, that's probably what happened. Okay, so this mapping failed. I guess I'm not sure exactly what line that's coming from. Alright. Oh, no, here's another mapping failed here. Okay, so we get down to this point and then mapping failed, and then it goes back to freeing TX descriptors and then processing RX completions. Well, let's take a look at the code. So this is the RX descriptor processing, or the RX ring processing. That is taking place here, where we are doing the refill RX buffers. So if this is going to be running, I mean, okay, let's think about how this works, right? What this should be doing is we take the difference between the producer and the consumer pointer, right? We subtract 128, or we subtract that out of 128. I guess this is actually a to-do, because that 128 should be the half of the ring size. We're only going to fill up half of the ring, just to make sure there's some available buffer space. I guess we could potentially fill up the whole ring, but for now I'm just going to do half. If missing is less than 8, we return. Now, for those of you not aware of what the heck this is for, this is basically a cache optimization. If we only have a couple of missing elements, we might as well just wait, because there's, you know, more stuff sitting in the queue. If there are multiple missing elements, then we'll go ahead and go through the motions of actually preparing those and inserting them into the queue. And the reason for doing this is that the CPU has a cache, right? So if we only want to run the code once, then we may need to pay some penalty for getting the code into the cache, and then at that point, well, we're done. So why do we pay that penalty? It would be better if we can batch, and then we can run, you know, several iterations here. We pay the penalty on the first iteration to get the code into the cache, but then at that point, we can just run. But it looks like what must be happening here is that this missing value is somehow becoming very large. But why could that be happening? Because we're taking the difference of these two. Now, one thing I should mention is that these pointers are assumed to roll over at a natural boundary. And this calculation should result in this this computed number of missing descriptors being, you know, a reasonable number that's relatively close to 0. But this is a U32, so these pointers, these should also be defined as a U32 for this to work properly. If they aren't, then that might be the problem. Oh, well, okay, these should all be U32. Yeah, because if that's a U16, then when you do the subtraction, you'll be generating a value near 65,000, which obviously is a problem here. Okay, well, great. We can increment the crash count again. I'll need to reboot that, and then we'll try it again. Let me see. Is this thing totally owned at this point? Oh, good. I can do the hard reboot this time. Okay, great. We'll do that. I've saved this. Let me see here. Where was my other script? Are syncing this stuff around here. Oh, I guess it was this one. Yeah, okay. Okay, so we'll reboot that, and we'll see if this solves the problem here. Yeah, so it's getting kernel drivers completely right is a tricky business. Oh, the other thing I should mention as well about why I'm doing this specific computation here, and that's because this is it's very simple computation to do, right? I'm not doing modulo operations. I don't have branches, things like that. It's just a couple of subtractions. And yeah, sure, you could probably do this in a quote-unquote safer way, but this code is on what we call the fast path, right? Because this has to touch every single packet that's coming or going. I mean, in this case, I guess it's not touching the packets directly, but it's setting up the buffers. So all of the code on the fast path has to be optimized, right? I mean, I guess from the standpoint of the Corundum Proto, it doesn't really matter, but for the full version of Corundum, it's very important that this code be as optimized as possible, because one, you want it small such that it fits into as few cache lines as possible, and two, you want this code to be very, very fast, because if it has to run for every single packet, every cycle that you're wasting is potentially a significant problem. Okay. Let's go ahead and take a look at this thing again. I think that was just a driver issue. I don't think we need to change anything in the hardware. All right, let's go ahead and rsync the files again. And I'm going to go ahead and get the D message running again. Okay, and go ahead and run a build here. Okay, and let me see notes, and I didn't want that one. I want there's ping or iperf or whatever. I think that's fine. I'll go ahead and I will add the IP address. Boom, and then we'll just try iperf, right? This was iperf 3-s. Run a server, and well, there we go. This seems to be running. Now, obviously, the performance is not particularly great, right? We're just running at a couple of gigabits per second. Oh, that's interesting. It started at about 1, and then it ramped up to closer to 2. And we lost the IP address again. Great. Network manager messing with us. That's always annoying. But yeah, okay. So that seems to work. So this is iperf running on my workstation machine, sending to the dev machine. So let's try to run that in reverse and see what happens. Well, that didn't get very far. It seems to have stopped at some point. So what happened here then? So, bad file descriptor. Well, okay. And this one is not sending anything, obviously. What happened? So we've got processing RX completion, pairing RX descriptor, so that seems fine. On the TX, we've done a bunch of cleanup, right? Cleaned up a bunch of stuff, so those packets got sent. We've got some trade-offs here, processing RX completion, pairing RX descriptor, that sort of thing. Free TX descriptor, so more stuff got sent. Prepare RX descriptor, that seems fine. TX ring full. Oh, shoot. So, I think I see what happened here, right? We're getting packets for transmit, getting packets for transmit, getting packets for transmit. We get TX ring full. At this point, what happens in TX code is, let me see. Right, when the TX is full, then we stop the transmit queue. But when we clean up the queue, where is this? The pull TXT queue, process TXT queue in here. We don't re-enable the queue. Yeah, okay. That's the problem. That's obviously not going to work very well. So basically, yeah, it turns off the queue because it was full to tell the operating system to stop giving me packets. But then we never started the queue again. So let's see. So after we've updated the pointers here, then what we need to do is re-enable the queue. So let me see here. So this is if netif tx queue stopped. So if queue is stopped, and this is priv tx queue, and we've actually done some work. Oops. Or the queue is empty. Oops. Priv tx queue cons, right? So let's see what we're doing here. If the queue is stopped and we've either freed some stuff or the queue is empty, then we need to wait the queue. Let's see, netif tx wake queue, and then this is priv tx queue. Okay, great. Let me see here. So I need to transfer that. Not sure if that's everything, but we'll give it a shot and we'll see what happens. All right, so cancel out of there. I'll do make. Oops. I don't know why it always complains about that. Anyway, whatever. Oops. Okay. There we go. Reloaded the module. Then we will try that again, right? And let me see here. iPerf and iPerf. There we go. 1 gigabit per second. Yeah. You might be wondering, why is this only running at 1 gigabit per second while the legacy version of Corundum can hit 10 gigabits per second, no problem at all? Well, this is because we have a very, very simplified code base here. And we're only handling 1 packet at a time for transmit and 1 packet at a time for receive. So you can see where the benefits of trying to do multiple things in parallel come from, right? You know, if we're only doing 1 thing at a time, we're only hitting a gigabit per second or so. And only lists 13 retries, but that's not exactly correct. Oh, no, I guess that's fine, because it's sending on this end and receiving on this end, right? So that feedback will be occurring internally. Actually, let me re-add the IP address. We'll run that again and make sure it's still working. Okay. Or do we get better results this time? Yeah, okay. These are a little bit more consistent now. And do we lose the IP again? I don't know. I don't know why this is being a little bit wonky, but anyway, we're getting a gigabit per second or so. So, you know, 1 packet at a time for 1500 byte frames, that works. But, you know, you get about a gigabit per second. Yeah, but for, if you actually want to get the full link rate, obviously you have to be able to handle multiple packets at a time. And similarly, if you want to handle small frames, the situation is going to be even worse. But okay, it's functional, and that's the whole point of the Corundum proto design. All right, so the next step then is to get that second port working. Yeah, so it's kind of saying that upstream the driver will take quite a few iterations. Yeah. So actually, the optimizations are one thing, but the real problem that I need to address, that's kind of on the to-do list, is basically decoupling the driver from the hardware as much as possible, right? I don't want to be poking at, you know, magic number addresses on the hardware, because that then you're totally screwed in terms of making any changes to the hardware going forward, because you have to maintain those same registers at those same addresses. But by using a different technique where you're using like commands that get pushed to the hardware instead, then you don't have that problem, and you can have significantly different implementations of the hardware, and, you know, have everything work correctly. So there's definitely going to be no upstreaming until, you know, that stuff is implemented. But yeah, that's the long-term goal, would be to do that. So Corundum Proto, that's just an educational thing. The whole point is that we can look at it and we can reason about it, you know, pretty easily. But all of the optimizations and whatnot, that's going to be implemented in, you know, Corundum Micro and Corundum Lite. And then those, you know, the driver for that will eventually be upstreamed, probably into both Linux and DPDK. But that's probably going to be a year or two before that happens. We'll see. Anyway, we have iPerf running in both directions. We have ping running pretty reliably. It seems like the pointer wraparound is doing what it's supposed to do now. So the next step then is to continue to work on the test bench logic here and get things cleaned up to the point where we can actually test some of this stuff in slightly nicer way, right? We want to make this look a little bit more like what the driver is doing. And if you've looked at the legacy version of Corundum, you know, you'll see what I mean. I've got a kind of an object model that sort of follows what the driver is doing. So that is, I think, the next step here. Once I have that sort of figured out, then the next step will be, after that, will be to get multiple ports working. Right now we have one port. The next step is basically to step and repeat the core logic to support multiple ports. So what I'm going to do for the time being is basically go the most straightforward route, which is not really the most optimal. And I'm just going to step and repeat the entire data path. So if we look at this core logic here, right, this has, it's got a basic control register interface here. It's got all of the internal DMA components. And basically what we're going to do is pull this into a separate port module, and then this is going to get step and repeated, once for each port. So it'll work, but we have a lot of copies of all of this internal logic, which is, it's not ideal, but it's fine for an educational project. Now, obviously, Corundum Lite and Corundum Micro are going to do things a little bit differently, potentially. So that's a problem to address on a different day, probably. Yeah, exactly. I got a comment here. So instead of register space, we're going to do a command queue. Yeah, that's the point. We'll have commands that get written out into host memory, and then those will be pulled by basically the same DMA subsystem that's used for the descriptors and whatnot. And then either we'll have like a state machine that process those, or they're going to be handed off to like a soft core of some sort. And then the idea is that you can be, in some sense, forwards and backwards compatible with these commands, because the state machine or the soft core can map those commands into what needs to be done in the internal register space. So there's still going to be registers, but you won't be able to, well, you'll probably be able to poke at them from the host in some way, but the driver will not be directly poking at most of the register space. Only a very limited and standardized portion of it. And then if you have like an old version of the driver with newer hardware, it just uses, the subset of commands that it's aware of, and vice versa, right? New driver with old hardware, it can figure out, okay, well, this hardware only supports these features, so I'm only going to use these commands. So that's kind of the idea. And then you can also have the driver, or have the hardware report information back to the driver in terms of, what offsets to use for the doorbell registers and things like that as part of the responses to the commands for setting up a queue or what have you. So there's a lot of advantages of going for this particular setup. And I know a lot of hardware works this way as well. So if you look at, NVMe devices, they have basically an administrative queue that you can use for allocating queues and doing other stuff, instead of having a big complicated register space. And it's a similar story with a lot of NICs. I know there's NICs that do have complicated register spaces, but for the most part, they're moving towards this command queue type setup. So, and with the experience I have working on the legacy version of Corundum, I can definitely see why they're doing that. So that's the long-term plan. All right, so where was I here? Okay, so I have this Corundum proto file that I created here. Let me take a look actually at the legacy version of Corundum really quick, just to refresh my memory of exactly how this fits together. Yeah, there was a whole collection of objects that were associated with this. So let me see. So there was that, and then when I pull this in, okay, got it. So what I'm going to do here is, I'm going to do that, and then, okay, here's the test bench. Okay, there we go. So somebody's asking, is this for 100 gigabits per second? So the Corundum proto design is, it's just intended to be functional. And for the boards I'm using right now, technically they support 10 gig and 25 gigabits per second, but from the iPerf results we were seeing a few minutes ago, it's only running at like 1 or 2 gigabits per second. So yeah, this design is not optimized for performance. It's set up to be easy to understand for educational purposes. But the idea is that we're basically going to take this design and use it as a starting point for iteration to work up to much higher link speeds. So yeah, the plan is to build Corundum Micro, which targets, maybe 1 gigabit up to 10 or 25 gigabits per second, and then Corundum Lite, which targets more of the 25 to 100 gigabit per second range. And the reason for having two designs is that you have to do things quite differently in terms of the internal optimization for that work. So yeah, as of right now, no, it's not targeting 100 gig, but that's going to be the plan in the future. Okay. And I guess the other thing I should mention as well is that Corundum Proto is also not really optimized for size. Corundum Micro is likely going to end up being a lot smaller than Corundum Proto. But, it takes time to implement these kinds of optimizations. Okay. So I've imported that file. The next thing I need to do now is to actually create some objects that can be used to manage all of the internal components. So let me think here for a second here. I need to create a driver object. Okay, and then I do self device. Okay. Okay. Okay, so what we can do now is I'm going to start moving code from the very basic test bench that I have here over into this driver that I'm putting together, this new Python script. So we're going to call init, and then we're going to call find device, and then we're going to do, let me see here. We're going to create the driver, and then we're going to do await driver dot, what do I call this? Init tstay device. Okay. All right. So when we do that, then we can actually start working our way through this here. So self-dot. I need references to a couple of things here. Right, so this need a reference to the pool, which will allow us to actually allocate resources. And then I'm going to do some of this initial stuff here. I'm going to go ahead and move this in here. So this goes ahead and it enables a device. It does set master, so we can use DMA, and it does some IRQ initialization. Yeah, okay, that's a good start. And then I need to create some references to the bars here. So this is going to be the main control bar. Okay. And then I can do, all right, so then this is going to do some more initialization here. So the reason I'm doing this like this is because if we add support for AXI devices later, which we probably will, although we'll see about that. I don't know about for Corundum Proto, but definitely for Corundum Lite and such. The first part of the initialization is a little bit different. And then the following stuff is going to be basically the same. All right, so we have the bar, and what do we need to do next? All right, so what I have here is all of this all of this code to allocate the, these are the queues, right? We have the args queue, tx queue, and the completion queues, and then we get into actually putting some stuff in those queues. So this one is, you can see here, we're allocating stuff from the memory pool. So what is going to be the best way to handle this? All right, well, the first thing I'm going to do actually is I'm going to get rid of, all right, I'll leave that there for now, because we're probably going to be actually using some of that. Go ahead and comment out that. I'm not sure exactly what else needs to be done here. Okay, so we have this for the overall driver. Inside of the driver, we're going to have to create looking at the old version of Corundum here. We have ports, we have interfaces. I guess I'll just create a port inside of this here for now here. Okay, class port. So the port will correspond to a net device here. One minor annoyance about Python is with I don't think you can create, or you can, I don't think you can make the constructor of something asynchronous. So because we need to write asynchronous code here for interacting with CocoaTV, you kind of have to split out part of the init code as a separate routine here. All right, so this is going to be self, and then we're going to call this maybe dev and index, and we'll call that regs. Okay. All right, so we can pass all that through. Okay. And then what we're going to do, at least for the time being, is I'm going to create a list here. Oh. Okay, that's fine. And then what I'm going to do here index 0 hardware regs self. Okay, there we go. So we create the port, and then we can initialize the port. Wait. And then you create a list for the ports. Okay, so self ports, create a list, and then I can go over here, self.ports.append port. Okay, great. So we've gone ahead, we've created the port. Okay. Let me think now. So we've created the port. Now inside of this port, we need to go ahead and set up all of the internal queues. So for the time being, what I'm going to do is copy all of this into this init step here. That what we want? Well, we'll start with that for now. Okay, so this is going to be dev.pool, right? Because that's what we've created here. Okay, and then all of these need to be moved. Okay, and these are all going to be self dot. Yeah, so I could create more structures here, or more objects, but I'm not going to do that for the time being. We're going to try to keep this relatively simple. Okay, so we've gone ahead and we've created the pointers here that correspond to the various regions, and I think this will work for setting everything up, at least initially. Okay, so the next thing that I need to do then, let me go ahead and get rid of this actually, that either. Oh, actually what I need to do is change all of these, yeah. Oh, dev.pool, that should be self.dev.pool. And then all of these are going to be self.hardwareregs. Okay, there we go. That's looking better. All those little red squigglies are now gone. This one is, I don't know what that's complaining about, because it should be imported up here, right? Yeah, okay. Anyway, all right. Okay, so what do I need to do next? So what I need to do next is to start filling up the queues. So for TX, we need to be able to take a packet and create a buffer for it and create a descriptor for it. And for RX, we need to do basically the same thing. We just need to allocate a buffer. And then, yeah, okay. So let me see, how did I do this before? I guess I had a very simple allocation setup. Okay. So just so we're not going completely crazy here, I'm going to do, so this is self.free packets. Is that okay? And then def alloc packet. All right, so if we have something in free packets, we return that. Otherwise, we do, we're going to allocate this, and I will go ahead and make it 4096 for now. Okay. Oh, there we go. Allocated packets here. And then we return that. Okay, cool. All right, and then similarly, okay, that's self.free packets dot end packet, and I guess we can do another assertion as well. But all right, so that's pretty straightforward. We can allocate a packet. That'll give us a buffer that we can use, and we can free that packet later. That way, we're not just exhausting resources inside of Python. All right, so somebody's asking, while building Corundum's RTL, what do we use to debug the the interface issues, like if PCI interface is not working or if the Ethernet MAC5 might not be working as expected? All kinds of different stuff, right? So obviously you try to work out as many issues in simulation as possible, but if you run into some sort of unexpected problem, you can start patching ILAs. You can't really get logging information directly from the HDL, but being able to look at register values and stuff can be quite helpful. So I have a utility that dumps the entire internal register state of Corundum. And that is quite useful for finding problems, because you can go through and go, okay, we kind of know what the register values should be. So if we don't see that, then obviously that's a problem, and we can go through and fix it. Or at least that gives you an idea of where to look. Let's see. Another thing that I've done is I've added HDL specifically for debugging. With the ILAs, for example, the triggering capability is usually pretty limited, so sometimes you'll write a few lines of HDL to generate a trigger signal for the ILA. You can also get a lot of information from statistics counters. So when various events happen, you can increment counters, and then you can read those counters either through the statistics subsystem, or you can just add some registers here or there. And I've also certainly just pulled out various internal signals on registers that you can then read via PCIe. And that generally works pretty well for debugging stuff. But yeah, sometimes you got to get pretty creative when it comes to debugging, because obviously you can't really see what's going on inside of the chip. So if you can't find a way to get visibility into what's going on, or at least be able to reason about what might be going on, it can be tricky. Anyway, let me just get back to this here. So we have some code to allocate and free packets. Next question is, let me see here. Let me see if I can run this again to make sure we're good here so far. This is not actually going to send and receive anything, but it should go through and do all of the init. Uh-oh. Oh, I see. That should just be import instead of from. All right, let me fix that. Okay. Okay. All right, so this didn't actually do much because I didn't wait for any of these write operations to complete, I think. Is there anything else that I missed here? So init common, this does call port.init, and it awaits that. Yeah, I guess what I should do is actually do an await. Okay, let's try that. Yeah, I guess as of right now, I'm not actually waiting for much of anything. Okay, there we go. We have all the rights to initialize everything. Okay, and I think those are the same as before, but okay, one step at a time. All right. Oh, and I guess some of these also need to be saved. So I'm gonna do, yeah. So this will be self.rxq, and here's rxcq and txcq and txq. Okay, great. And all of these are going to be self dot whatever. Okay. See here, maybe I'll do that. Okay, there we go. That's a little better. All right. Yeah, I guess so far on this particular project, I haven't had to use any really weird debugging techniques, but I've definitely had to do some funky stuff in the past. Okay, so that looks good. Everything is saved, so now we can look at actually sending and receiving packets. So let's go ahead and implement sending first, because that's a little bit more straightforward, I think. And then the next step would be to implement the receive side. So this is the core of what needs to be done. I think here I need to do async start xmit. All right. Okay, and then we're going to have that in like that. All right, so this is going to be self.dev.alloc packet, and then the, see here. What's the best way of handling this? Okay, so what we're going to do is actually, I'm going to emulate what the Linux kernel does here. I'm going to call that data. Okay, there we go. It's going to be over here, right? Data. Okay. So what is it with these 10s? That is related to how the Linux kernel actually lays things out in memory. It's very common for packets to not actually be aligned at the start of a page, but have a bit of an offset. And this is done for a couple of reasons. One, by having an offset that is a multiple of 4 plus 2, or 2 bytes offset from multiple 4, it means that everything following the Ethernet header will be D-word aligned. So you can do an offset of 2, 6, 10, etc. Those would all satisfy that constraint. But they also usually have an offset because if you want to insert headers, if you have some space to do that, like if you want to add a VLAN tag or something, if you have some space to do that, then you don't need to move the entire packet. You just need to move the header. And that saves a lot of CPU cycles. So by emulating that in the test bench, we can ensure that when we actually load this thing on the card, it's going to do the appropriate thing. Oh, actually, I guess I do have this right thing. Okay, great. I'll just do that. I'm trying to outsmart myself. That doesn't help. All right. So self.txq.write. Okay, so this is being written at the production point, the producer pointer, right? So self.txq prod, right? And then this will be self.txq prod plus equals 1. All right, great. And this will be self.hardware rigs. So we write that, and this is again self.txq prod. Okay, you make sure to mask that off appropriately. I'm not going to bother with that. I think that's fine. Struct, all right, I'll need to import that, and then this is going to be data. Okay, and a txbuff.get absolute address. Okay, this is all looking pretty good. I just need to import struct. Oops. Hitting the wrong keys. Okay. Okay, that's fine. And now I should be able to do, let's see, await driver.port0.start IT, and then I can just give it some, let's use the same test data we used before, right? And we'll see if that works. And then I need to wait for a while, don't I? Okay. Oh, okay. So what we actually need to do now is I need to add plus 10. Try that again. But I think that should work. Yep, there we go. Perfect. In fact, what I'm actually going to do, be a little explicit about this. I take that 10 and that one. Okay, there we go. So now we have an explicit headroom. Okay, so we no longer have this random magic 10 in here. Okay, but that works. So now with this, we should be able to say send 10 packets or something, right? So if I wanted to send 10 packets, then I could put this in a loop, right? I could do 4. Right, we can do something like that, and then we should be able to see 10 packets get sent. Although I guess the question is, what did I set the queue size to? I should take a look at that. So there's 1, there's 2, there's 3, there's 4. Okay. This is sent a few. But I do need to check on that because I think, well, there could be a flow control problem, but that's a different issue. All right, so I think there's actually 2 other things that I need to do here really quick here. And I need to actually translate these back to the driver. And this one is I need to specify the queue size, self.rxq size, and then I'm gonna make this 256 again. And then rxq mask, and this is gonna be self.rx, all right, rxq size -1. Okay, let me check on how this was done over here briefly. Oh, I guess this is done up here, isn't it? How did I do this? Ah, okay, I see. Well, I'll just do that for now. That's not quite correct, but we'll roll with it. Okay. So this is a TXCQ. Okay, and this is a TXQ. And this is RXQ. Or RXCQ. Actually, I guess I do need that now that I think about it. Alright. Let me do this properly. Alright, so what we're going to do, I need a log size. And this is going to be some number, right? Bit length. -1, and then RXQ size is 2 to the log size. Okay, great. So that's that, and let me go ahead and duplicate this. So for these guys is the CQs. Okay, and this is the transmit queues, and this is the transmit completion queues. Okay. Oops, this should be transmit queue. Okay, great. All right, so the size and the log size need to be specified somewhere. So how did I do this again here? Oh, I see. And I have these doubled up. All right, so I can get rid of all of these. And this is going to be... self.rx or rxq log size shift by 16. Okay. That's C, that's C, that's TX, that's TX. All right, so that's how we set the size of these things. Okay, and then when, let's see, so the producer pointer, that's fine. Okay, but this is not correct because we want to do the index, and the index is going to be the producer pointer, but we need to mask it, right? Well, so that. All right, so we did mask that. We want to mask it by self.txq mask. Okay, there we go. So this is important to make sure that we're computing all the indices correctly, right? Because we want to take the producer pointer and we want to mask off the low order bits to determine the index, and then we write the descriptor to that index. Right, okay, so that makes sense. And then over here, we write the producer pointer, we mask off because in hardware, the pointer is only 16 bits. Okay. And then for these queues, right, we have the log size is the, well, it's the log base 2 of the size, right? So for 256 bits, the log size should be 8. Let's just double check that, right? So if I do 256 dot bit length, yeah, -1, you get 8. Perfect. So this is basically the Python equivalent of the clog2 in Verilog. So that gives you the number of bits. So 256, that fits into 8 bits. And then the queue size is 2 to the power of the log size. The mask is, -1 of that, right? So if you do 2 to the 8, what do you get? You get 256 -1, you get 255, right? Well, what is that in hex? Well, that's, that's all ones. So some basic bit manipulation techniques there. So yeah, the size mask is then used to determine the index inside of the queue. Straightforward enough, probably. Okay, so that is the start transmit. Obviously we got to do all the cleanup and such too, but I'll implement that later. For the time being, I just want to be able to do some simple tests here where we can queue up some packets for transmission. Well, all right, let me just see here. Maybe I can do a little bit more than this without too much difficulty. Let me remind myself how the interrupt handler works here. Okay, I see. Okay, so what I'm going to start by doing here is I'm going to implement an interrupt handler routine here. Let's see here. All right, self-index. Okay, that looks good. All right, well, that's fine. We're just going to do a pass for now. So the idea is that this interrupt handler, we're going to be able to run all of the cleanup stuff. So, well, all of the cleanup, and then also handling the packets on the receive path. So when we go ahead and we create the, where is this here? When we create the port, at some point we need to actually allocate the interrupt here. So where was that done? All right, so that, I think I will do that. Yeah, that should be fine. Self.dev.request IRQ. Okay, so I'm just going to do 0 and then port.interrupt handler. Okay, I think that will work. Well, we'll see. I might need to reorganize some stuff. I think the I think for AXI things are handled differently, but this should be at least a starting point. All right, so in the interrupt handler, there's a couple things we're going to need to do. One of them is we'll have to process the TXCQ. We got to process the TXCQ. We got to process the RXCQ. We also need to fill the RXQ with buffers. It's probably a couple of other things. Hey, let me see here. There's RXCQ, and there's going to be the TXCQ. Oops. All right, so RXCQ and TXCQ, I'll go ahead and call both of those from here. Self. And then again for TX. Okay. So when the interrupt handler fires off, then these will run. I guess the other thing I need to do really quick here is to handle logging so we can actually see what's going on. How was this done here? Okay. All right. That looks all right. And then how did I do this, like with the device? I think I made a copy of it. Yeah. Okay, so make a copy of that, and then we can log stuff. So I can do self.log.info that, and that I think will show up correctly here. Yeah, so we can see the MSI interrupt getting fired off at the root complex level, but oops, okay. I need to import logging as well. But what we need to do is see that call making its way all the way into the actual driver model. Well, that's interesting. I don't think it was complaining about that before. Did I forget to await something? What happened? Seems like it didn't, maybe didn't properly set up the MSI interrupts. Oh boy. Wait, is this actually the right address? So the last time this ran... If I scroll up enough here. Okay, that was the same address, so that's weird. Yeah, I guess to figure this out, I might need to go digging into the PCA code a little bit more deeply to figure out what happened here. So this was related to request IRQ. If I comment that out, is it okay? Yeah, I guess things are being done in a different sequence. So I need to take a look and figure out what happened. Alright, well, I will table that for the time being. This code, it still needs some more work. What I want to do is move on to getting multiple ports working. So we can only test transmit with this current setup, but at least that's something. So this needs some more work. I need to put some more time into kind of debugging and cleaning things up, but this does work for sending multiple packets here. And I guess, do I still have this open? If I hit a refresher on here. Oh, this was for the board level thing. Okay, right. So if I open this for the top level test that I've been working on, we can take a quick peek and see if everything looks okay. Open default app, that should open it in Surfer. Okay, great. Let's take a look. If I go into the, where is this? For instance, go into, how about the transmit path? Why not? Well, all right. I'll actually look at the descriptor read module and we'll see what that looks like. Okay. All right. So we can see it be enabled. We've got the log size set to 8. And then we've got 1, 2, 3, 4. Well, yeah, we've got 10 packets being sent right here. So that definitely seems to be doing what it's supposed to do. And we can see the producer pointer incremented a bunch of times as each packet is written. It's as the way the code is written right now, it writes that update pointer every single time it enqueues a packet. So see that from the test bench, the packets get enqueued, and then the packets get sent. Bing, 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 bing. You know, it takes a little bit of time for each DMA operation to take place before it moves on to the next one. Now again, this is only doing one packet at a time. If we were doing multiple packets at a time, then you would see a bunch of packets start, and then as those, we'd see a bunch of packets starting until it filled up, you know, the internal resources for tracking, you know, parallel operations, and then you would see other operations starting as those resources were released. So it would look kind of like this. You get a bunch of stuff starting, and then it would look like this afterwards, where things are more spaced out. So, but with the way this is set up here, right, simplified. So this is what we get. All right. So the next step then is to look at implementing multiple ports. And how are we going to do that? Well, what I'm going to do is I'm going to take the simple approach here, and I'm basically going to duplicate the entire core logic several times, and I'm going to add all of the multiplexing logic to make that work, right? So we're going to take, so for the DMA stuff, that's pretty straightforward. For the bar space, what we have to do is add a AXI interconnect module, which can, you know, route the register operations appropriately. So what I'm going to start by doing is making a copy of this. I'm going to call this port. Right, so this is going to have basically all the same stuff in it. Oops. All right, so this is going to be the port logic here. Okay, and the port logic is only going to take one port. Right, so I don't need the port value here. Actually, I'm going to leave it just as a placeholder, but the plan will be to get rid of that. Okay, so we've got the AXI Lite interface here, we've got the DMA stuff here, we've got IRQ, right, 1 bit, that's pretty straightforward. Okay. The next thing I need to do actually is I want to make this per port, right? And do anything here? I think. Oh, actually, this should be. Okay. So I can do that. That should be fine. Oh, actually, that also means that I got this backwards. This port needs to go over here. Okay. Oh, that should be ports. Okay. All right. I'll clean up the alignment later, but there we go. We have that, and now what I need to do is to actually set up the control registers here and instantiate the port module. Did I rename this? Okay, that is port. That's good. Got all this. I think the rest of this is basically fine as it is. I shouldn't need to touch anything else in here. I don't think. Yeah. Okay. So that looks good. Now I need to go over to the core logic, and I'm basically going to delete everything except the register interface. And then we'll instantiate the core logic in here. Okay. And let me see here. I can vastly simplify this. I'm just going to delete everything except for, I'm just going to comment everything out, right? Because what we do need to do is somehow indicate to the driver, you know, how many ports there are. So a lot of this stuff can go away here. This is going to have to get reworked as well, but one step at a time. That's fine. All of these go away. And okay. Okay, so now I go over to port, and we can take this entire top level block here, copy that. I will go over to core now, and I need a for loop here, right? For E is less than ports, and okay, cool. Oh. All right, so there's the port, and it's going to be port inst. All right, so clock and reset, that's fine. This one I got to figure out. This one I got to figure out. These are pretty straightforward, right? Because these are just going to match the top level, but we're going to pull out the port here, and same thing here. Okay, that looks good. This one, I think actually the same thing, right? So IRQ. Okay, great. Okay, so now what I need to do is to add, let me see here. All right, there's a couple things that I need. So I need a that's going to be useful, and I also need okay, the port offset. This is where the ports start, and now I need to create a an AXI Lite interface and AXI Lite interconnect for hooking everything up. So we're going to go ahead, and I'm just going to copy this from this other file I have lying around. So this is going to be the AXI Lite interface that connects to the internal stuff, right? We've got ports and port offset. So port offset is going to be 1 because we need to have some kind of top level control registers. And ports, that's the number of ports that we have. So we put those together, that's what you get. Then we have an AXI Lite interconnect here. We're wiring this up to, oh right, this is not the number of ports necessarily. This is based on the number of elements in this interface array. So another thing I'll mention is that I just created a new set of wrappers around the AXI Lite interconnect module, because one annoyance of System Verilog is that if there's a difference between an interface array of length 1 and just a bare interface, which is quite annoying because as much as it would be nice to be able to connect an interface to a port that accepts an interface array of length 1, there isn't a nice way of doing that. So I went ahead and created these wrappers that handle that internally, just to make things a little bit easier to deal with. So yeah, this one is specifically just has a single interface on the input side, and some of these other components are a bit more simplified. Some of the parameters are simplified to reflect that. Okay, so that's that. And then what I need to do is, let me see here. These all need to be passed through to the new control interface instead. These are going to go to 0, and then the ports are going to go to the higher numbers, right? So AXI light control. Oh, actually, I don't have a difference between read and write now, do I? Okay, there we go. Okay, so that should be enough for this. I don't need to worry about the write for now, but I am going to implement a couple of registers on the read side. Okay, so this is going to be, so we'll expose the port count, and then I need two other things here. No, one more. Okay, there we go. All right, so that is going to be, so we need the offset and the stride, right? Right, so the offset is the AXI light internal address of the first port. The stride is then the step to the subsequent ports. And these are the same because we're reserving a block for these internal registers that we're looking at now. And that's going to be the same size as the region that each port gets. So just keeping things very, very simple here. And this has to match the configuration of the AXI Lite interconnect. So we're setting it up to allocate 16 bits of address space to each one of the downstream ports. So we get 16 for the control registers, and then 16 for all of the ports. So these values are going to be used in the driver and also in the test bench to be able to connect to all of the individual ports. All right, what else do I need to do here? Like I said, this is a stand-in parameter, so I'm going to leave that as is for now. It's not necessary, but it's like when we add more stuff later, then it'll be nice to have a place to put that stuff, and then we can delete that at that point. All right, then what I need to do is pass these through, and this is going to be ports. No, this is port offset plus P. Perfect. Okay. And then for the DMA interconnections, there's a bunch of stuff that I basically would have to copy from the from here, right? Because in this case we have the descriptor interface and the RAM interface and such for all of the DMA connections, and then we have the DMA interface muxes as well. So I spent a lot of time typing these up before, but I have them over in this separate file that I can just go ahead and paste in to save a lot of typing. So what we have here is the DMA read descriptor interface here. We've got the write descriptor interface here. And then this is the DMA RAM interface for both reads and writes, and then the DMA interface descriptor mux. And all of this is based on the number of ports. So if we have 2 ports, then there's going to be 2 of these internal interfaces that get passed around. 2 of these, and 2 of these. And this DMA interface mux is then used to multiplex operations from both the ports. So that's, it's pretty straightforward. And then over here, I need to go ahead and plug in all of this. So how did I name things here? I think for these it's just DMA RAM int, and for these I think this is just int as well. Yeah, read descriptor int, write descriptor int, DMA RAM int. Yeah, okay, that looks good. All right, so that's looking pretty good. Now I need to go ahead and update this. I need to add a couple of things. I need to add the port module here. Right, do that, and then under AXI, actually I can replace the AXI. Oh, I can get rid of that one. This is going to be AXIL. This interconnect 1s.f. I think that's what I need, right? Not 100% sure, but we'll try that. Now this test bench is not going to run correctly. Hopefully will build. If it doesn't build, we'll need to look into something. Oh, okay. Signal definition not found. Oh, 290 in what file is that? Corundum Proto Core 290. Oh, this should just be P. Alright. Okay. Uh-oh. Something is unhappy here. What happened? Ah, okay, I see. I forgot about that. When I converted these things from individual ports to interface, or from interface arrays to individual ports, I now need to go through and delete a couple of array dereferences here. Okay. Is that everything I need to do? There may be some other stuff that needs to be handled. Okay, something is still unhappy here. Oh, DMA IF mux. Alright. Okay, so that goes away, and there we go. Okay. Something is still unhappy. Alright, so... Okay, I think there's something else I need to adjust. Where was that? So this is looking at... Wait, why is it UUT? Shouldn't be UUT, right? One moment, where is this? Why do I have something called UUT? Oh no, I guess that's fine, okay. MSI inst arb inst. Where was the MSI block here? Oh, this has got to be a this has got to be a verilator bug. What the heck? This doesn't make any sense, right? Because this is reporting a problem in the DMA descriptor interface, and this says in instance that this is something completely unrelated. So this is tripping me up because this is complaining about an arbiter instance, but there's no relation between these two. So, well, boy, I don't know how you put together a minimal example for that, but that's a problem in verilator. That's reporting that against the wrong module. Okay. That simplifies things a little bit. So this is complaining about, I think, wait, where is this? I think it might be in here somewhere. I think I have some offsets that are not quite correct. So I think I need to remove this and this, maybe. Or 17 warnings. Let me see if this does much. Oh, the other thing potentially is that I actually need to make some stuff wider here. Yeah, that might be what I need to do here. Let me see if that does anything useful. Okay, 18 errors. That solved a few problems. Mismatch between port which is an interface and expression which is not an interface. Oh. Yeah, okay. I see what I did there. Again, I forgot to dereference these things properly. So these are all going to be, there we go. Is that everything? Somehow I doubt it, but hey, that might actually be working. Okay, cool. So with that running, let me locate my Vivado build here. No, it wasn't that one. Let me actually close that one. Don't need that. Get rid of that guy. That was that. What am I doing here? Oh, I was copying some stuff around. Okay. I don't need that, do I? Okay. Okay. There's Vivado. All right. So I'm going to go ahead and kick off the build, and we're going to see what that does. I have confidence that this is going to work, but we'll see. What I do need to do is add some code to read some of these settings. So this is where we can go now into the Corundum Proto Python script, and this should simplify a few things a little bit here. Because what we can do is we can read, yeah, what we can do is fetch the register settings that we just implemented. Where do we need to do that? We need to do that here. Yeah, init comment. Yes, perfect. We need to do that here. Okay, so we do self.port count, and this is going to be read keyword. And I think I put this at 100. Okay, perfect. Right, so we get the port count, we get the port offset, and the port stride. Okay, so port count, port offset, port stride will be 104 and 108. We can read all those, and I'm going to go ahead and print these out as well so we can see exactly what's going on. Okay, and then I'm going to make these hex so we can see exactly what's going on there. Okay, great. So it didn't run, which is expected. But let me see if this now reports the offset correctly. Yeah, there we go. Port count 2, port offset, port stride. So we have values here. Now what I need to do is I cannot pass through this hardware regs directly. What I need to do at this point is compute what that address is actually going to be. And it's not a matter of just computing the address, but I actually need to call something to create a window that can be passed down. So we'll check how to do that. Let me see here. System resources. Apologies if there's some jitters in the screen. Okay, that's what I need to do. All right, so I do hardware regs dot create window, and then I do self dot port offset. Okay, and then what I can do actually is a 4K in range self dot port count. Okay, and then this will be plus self dot port stride times K, and then this is also K over here. This eventually will also be K once I get that figured out. All right. Let me try rerunning that and we'll see what happens. Oh. Missed a colon. Okay, so that looks like it actually worked. We can see, looking at the, let me see here, what was this one? XCC frame. Oh, okay, I see. Okay, so we can see this is initializing the first port, and this is initializing the second port, and we can see the register reads up here that are that correspond to reading those these configuration registers, these informational registers. So we've read the port count 2, we've read the offset, we've read the stride, and then based on this information, we can create the ports. So that's that seems pretty reasonable. And now for now, we're only using one port. What I can do next is fire some stuff out on the second port, and we can see if that works. Let me take a look and see if we can fire off stuff on the other port as well. So if I do port 1, oops, port 1, not port 2. Let me see here. On port 1. Okay, perfect. Now, this should actually interleave the transmissions between the two ports. Yeah, so here's port 1, another on port 1, here's port 2, port 1, yeah, so we can see frames going out on both ports. So, hey, that looks pretty good. And we can also see the MSI interrupts being issued on the different channels. So here's issue MSI interrupt index 1, issue MSI interrupt index 0, and I think, yeah, here we go. We can also see the data being changed at the root complex level, right? So here's the MSI interrupt for index 1 and the MSI interrupt for index 0. So all of that looks good. I'm not sure why as soon as I try to register that, register the interrupt handler, that things start breaking. So I need to take a look at that. That might be a bug in the CocoaTV PCI Express extension, but what are you going to do? But this is looking pretty reasonable. So let me take a look at what Vivado is up to. Vivado is waiting on synthesis stuff. All right. I think it's working on synthesizing the IP cores and such. So we'll give that a few more minutes and we'll see what happens there. I also need to start making some modifications to the driver to support operating in this mode. So let me take a look now at, oh, I don't want that. I want this, okay. All right, so here's what we're going to do. I am going to, let me see here. Okay, this is priv for Corundum. Where's the device? Corundum Dev. Okay, there we go. This is what I want. The priv, I'm going to call this HW regs, and this is not going to be barlen. And I'll leave that one alone for now. So that's one change that I want to make. This is just to make sure that I'm hitting that in all the right spots. The next thing here is to add a couple of, I don't need RQ count, I'm not using that right now. Okay, so this is, I want U32 port count, U32 port offset, 32 port stride. Okay, great. That looks pretty good. And net device, I'm also going to make this an array. We'll do that for now. Okay. We have to create multiple net devices for that to work. I think I have, where was that window? Wasn't that window? Okay. So what I can do here is do a test build of the driver and see what all needs to be fixed. Okay, yeah, I need to go update things in a number of places for this to work. Yeah, okay. So let's start working on this piece by piece. So instead of this, I need to do a for loop. Both of these do a for loop here. So I need to do int k and int k. All right, so I'm going to do for k, oops, for k equals 0, k is less than, actually I guess I need to make that a little bigger number than this needs to match. I think there's a different, I need to look and see if there's a better way of doing this so I don't have a constant in here, but we'll do this for now. I think there's an array size macro. I'll have to look that up. Okay, so we do that, and then we're going to do, I need to move the PCI free IRQ, and this is going to be K. And then we also need to destroy netdev here, and be looking at K. And then we can set this to null just to make sure. Good. Okay, that goes away. All right. And I can copy this over here. Okay. And I actually need to put this up here because if any netdev fails, we need to clear out the previous ones. Okay. I think that's what I need to do there. And this one, I need to move the IRQ into the netdev, so I'm going to go ahead and do that. Is that right? Yeah, I think that's right. Okay. That looks reasonable. Okay. The other thing I need to do as well is I need to read these registers, right? So after allocating the IRQ vectors, then I'm going to start by commenting all of this out for now. And I can do cdev port count. It's going to be IO 32. And this is looking at cdev bar So then I read the 3, so there's 4 and then 8, and I'm reading the offset and the stride here. Okay, great. And then we can go ahead and print these out. So I can do dev info, and before I actually run anything and try to make the net devices, I need to make sure that it's actually reading things correctly here. So port count. Alright, so let's count, and then I do the same thing here for offset, and oops, and stride. Let's work. Right. Okay, and this is again 0x at x, so we have it at x. Perfect. Okay. Okay, so hierarchy count. All right, so I'm going to go ahead and I'm going to comment this out because we're not using that now. I need to move that into the device. Okay, so there's a bunch of stuff that I need to fix in here because we're looking at where was that? Right, we're looking at div bar. That all needs to be replaced for the hardware address here. And I remove that. Okay. So another thing I need to do as well is I need to set this up to accept a couple of parameters here, right? So I need int port, and I need to void IOMEM hardware address. Right, so this is then going to be the hardware address here. And the port, that needs to be, what do I do with the port? That needs to be specified somewhere. Yeah, all right, so set netdev dev. All right, so this is ndev dev port, set port. And this is important for actually generating the network device names correctly at the operating system level. Oh, what is this complaining about? I don't know what that's complaining about. I think it's confused about this IOMEM thing, but that's a Linux kernel thing. Okay, what was the next thing I need to do here? Right, I need to update this in the header file for one. So this is create netdev. Yep, that goes here, and then right now that's, I think I commented out the call for that. So okay, that works. And let me see what else needs to be done. I think I need some modifications in. Oh, I didn't save this file, did I? Where is this complaining about that? Oh, nice. What is this complaining about now? Hardware address. Oh, hardware rigs. Got that name wrong. Okay, cool. Let me try that. How did I do that before? All right, I guess I did. I guess I did that. I can't remember exactly what I did. Okay, anyway. Let me see if that's happy. Okay, that seems fine. I just have a couple more things to need fixed here. So in looks like I need to fix something in a TX, and then I'm thinking I also need to make the same equivalent change in RX. Oops. Okay. Okay, so that seemed to work. Now I just need to see if Vivato's done. When that's done, then we can try the two-port design. Oh, man, all right. It's not happy about something. RTL elaboration failed. What happened here? Invalid index for scalar. 98. Oh, yeah, okay. This is another variator bug. Actually, might have been one of those. Yep, okay. Okay. Yeah, Verilator, for whatever reason, has some issues when handling interface arrays, and it will not complain if you don't dereference it, but Vivado requires you to dereference it. So I think that needs to be tightened up a bit in Verilator. I guess the real question is what the LRM says, and I'm not super familiar with the system Verilog LRM specifically, so I reported a while ago. I don't think it's been fixed yet. Alright, so that'll take a few minutes to build, but the well, let's just go ahead and see if I can figure out everything else that needs to be done here. I need to add an interrupt to the net device, right? Because we're moving the interface, or we're moving the interrupt from the, see here, what am I doing here? Yeah, so I'll comment this out here because what I want to do is move this into the net device, and then only register the interrupt when needed. Okay, so that looks fine. We got IRQ and we got the data. So C proto dev, we can get that. Oh, actually, this is going to be net device. Yeah. Net device. That'll be ndev equals data, and then this is net dev priv. Get that. We get rid of that. Interrupt. We can do net dev info. The ndev, right? We get the interrupt, and I can get rid of that. I can get rid of that because we have the priv already. Oh. Be priv. Okay. Priv. Okay. Right, we get that. We have the priv port up. Then we can go ahead and do that. Okay. I think that's everything. So that's basically what we're doing before, except we're going to have a different IRQ for each net device. And by handling it locally, I think it's going to simplify a few things. So what I need to do now, I'm going to go ahead and write the code that I think I need for this, and then we'll take it one at a time. As soon as the Vivado build is done, it looks like it worked that time, right? It's working on, yeah, it looks like it completed the elaboration anyway. Okay, so I need a for loop here. K is less than cdev. Oops. Port count. Net device. Dev. I don't need to set that equal to anything yet. Well, all right. Got to keep it a little bit short, right? DM. Oh, wait, no, C Pro. 8 net dev. All right, so this is cdev. Then K. And then what is this? So we get bar, then we add cdev port offset plus cdev port pride times K. Okay. We'll make sure that this is properly nested. And we can do if, is, error, or null. So if that failed, we have to deal with that, right? So ret pointer error. That failed, then we go to fail netdev to clean everything up. Ret equals PCI request IRQ. Let's see here. So this is going to create the IRQ. Let me actually double check to make sure I got this right. Yeah, okay. But I do need to copy this then into the header file. Did I declare that as static? I did. I need to do that. Where was the header file? Okay. That goes over here. I will put it right there. Okay. So I've requested the IRQ. I have the IRQ handler there. If ret is less than 0, then we got to do something about that. Oh, this should not be error. This should be info. Okay. That goes to fail netdev. All right, and then in this case, I need to do proto destroy netdev. Okay, and this is ndev. Okay, and this is failed to request IRQ. And then the last thing we need to do here is to actually save this thing here. cdev ndev k equals ndev. Okay. Is that everything? Yeah, okay. So we create the net device. If that failed, we return the error and we go to fail net device to clean up. If that worked, then we request the IRQ, right? We point that at the net device. cproto IRQ is this guy, so that looks good, and we are pulling out the net device and then the priv, and then we do that. Okay, that looks good. Let's see, if that fails, then we print an error. We go to, well, we have to destroy the net device that we just created, then we go to fail netdev. Over here is fail netdev where we clear that out. Okay, fail IRQ. I guess we don't need that anymore. Okay. Let me see if I can do a test build here and see if that looks okay, or if I screwed something else up, which is a high probability. Okay. Okay, so that seems to have worked. I guess now it's just a question of, let me see here. Now we just wait for Vivado to do its thing. Well, all right, so while Vivado is running, I guess I can take a look at that issue with the interrupt. Wait, let me think about that here. Oh, actually, there's a couple other things I need to do to the driver, right? So in the in the test bench, we created these additional parameters, I guess, here, right, for the log size, the size, and the mask. So we should do the same thing in the header file here for these. Let's see, where are we? Producer pointer. Let me go ahead and I will duplicate all of these for log size, and mask. Okay, so we need to go ahead and do the same thing for all of these guys here. And then these need to be used in a bunch of different places. So I remember adding a bunch of to-dos in various places, so now we can go ahead and resolve some of those. Let me see here. I'm going to go ahead and grab these guys. I'm going to go to NetDev for now. Okay, so the log size. We double check how to do this. I think there's a kernel. Was it ilog2? Oh, I'm looking at the wrong file. Yeah. Okay. So this is going to be ilog2 256, and then the RxQ size is the log size. So just that, I think so. And the RxQ mask will be the RxQ size -1. TXQ, oops, not quite. I need to get all these correct here. All right, so that's TXQ, and then RxCQ, and finally TXCQ. Okay, great. With all that specified, then I can start using some of these values in the appropriate locations. So like for these, instead of doing that, we're going to do for priv RxQ log size, right? And then it's going to be TXQ, RxCQ, and TXCQ. So we can do that to set all the sizes correctly. Right. Oh, that's actually one other thing I should do as well, is all the region lengths. These can come from the sizes. So this one will be times 16, right? That's TXQ, not log size, but size. Okay. There's your RxQ, and then the TXCQ, and the RxCQ. Yeah, so all of this stuff, slowly works its way in here. Okay, so this is, again, this is based on the TXQ size, and this is the RxQ size. Let me actually just take a look at this code that we put together before as well. I think, yeah, the allocations can be fixed here. It was 4 times 1024. Why did I do that? Oh, the page size, right? Okay. This would be self RxQ size times 16, and this is then RxCQ, and again TXQ and TXCQ. There we go. So we can specify all of that as well. Okay. Going back to, where was I? So that was here. So I have all of that specified. Now I need to start going through some of these other to-dos that I had specified. I think it's mainly in terms of masking stuff. So if I go to say RX, that's fine, but this one should be a mask here, right? So this should be priv RxQ mask. Okay, I think that's fine. And then for TX, this would be the same thing, right? This is going to be TXQ mask. All right, this is TXQ mask. TXCQ mask. Now I guess what I need to do is fix up this phase. Oh no, that's correct. No, this is right, but the cons pointer here. How was I doing that before? All right, that's just based on the size. Oh, this should be TXQ size. TXCQ size. Yeah, okay, there we go. All right, then again, I got to do the same sort of stuff over here. So, let me see here. So this one again, this is RxQ mask, and there should be at least a couple more of these, I think. Yeah, this is going to be RxCQ mask. Okay, and then this is RxCQ size. Okay. And this RxQ mask here. Okay, what else do I need to fix? That's looking pretty good, actually. So I think there's still a few other little odds and ends that need to be cleaned up, but for the most part, this is looking more reasonable. Big thing is that all of the magic numbers are slowly going away. Yeah, now we're just waiting on Bravado to do its thing so we can try out this multi-port design. What are we doing now? Oh, so this has completed the routing, so hopefully in a couple minutes we'll have a bit file that we can test. Excellent. Yeah, it's still having issues just right around the PCI Express IP core itself because of how the clock domain crossing is handled internal to the Xilinx PCIe core. So the problem is that with the Xilinx PCIe IP core, it seems to be running the core at 500 megahertz, and I don't necessarily think they have the most optimal timing constraint setup, because basically those traces get constrained for 500 megahertz, or those nets get constrained for 500 megahertz, even though the core clock is only 250. So that causes a little bit of trouble. So previously I had added I'd added some register slices on what was the port? It was the sequence number port for the RQ interface, which is a start. But the problems that we're seeing now, I think, are on the rest of it, right? So we're looking at like the address reg and op count and a few other things. So I have to take a look at the full timing reports to figure out exactly what's going on here. But these they're all in the DMA engine. Yeah, we're looking at final completion record. So this is like, where is this coming from then? I think this is coming from information on, I guess it'd be RC actually, because that's coming from the core. So these are probably in terms of computing what the next DMA transfer is going to be based on how much data it got. We're looking at the read DMA, it has to do some computations for that. Anyway, looks like we have a bit file now. So let's go ahead and actually let me make sure that the driver is unloaded. So we will go ahead and do that. It's now unloaded, and let's go ahead and program. Apparently I thought it was out of date for some reason. So, okay, good thing I checked, because that would have taken a while to rebuild. Although hopefully that wasn't spurious. So, we'll see. Let me see. I think for the driver, I'm going to comment out the actual creation of the net devices for the time being, just to make sure that those register values are being read correctly. All right, where was that window? Okay, here we go. I'm going to go ahead and transfer that to... Transfer that over. All right, make clean and make. Good thing good thing I did that like that. Okay, I need to reset the card first before this is going to work. Actually, here's what I'm going to do. I'm going to add one more thing here. Let me think. Got a map bar 0. I like inner vectors. All right, so I'm going to do that check here. This is going to prevent some kernel crashes here, right? So if we read this and we get all Fs, read the first register in here. That says device needs to be reset. Okay. All right. I think that will work. Oh, I don't. Yeah, that's fine. Okay. Let's try this again. Let's see if we get. Oops. Why complaining about those files? But anyway. There we go. We now get an error. Device needs to be reset. Perfect. Okay. So I'm going to go ahead and RM mod that, and then what happened? Hmm. Well, I don't have an explanation for why that failed, but okay. I guess I need to do another hard reboot. Ah. IO unmap bad address. But it did map it correctly, so why would it be complaining about that? That doesn't make any sense. And here I was hoping to prevent a crash. That did not work as expected. I think I had a similar check in legacy version of Corundum, so where did that take place exactly? That must be on the PCIe side here. PCIe probe. Yeah, it's all the way down here. Device needs to be reset. And it's after stuff is mapped. So this is doing on PCI IO remap bar. PCI IO remap bar. I'm doing the same thing. Oh, okay, maybe I forgot to return an error code indicating that something failed. That may be what happened. Yeah, yep. Okay, that's probably what happened then. All right. There we go. Modules. Go ahead and rebuild that, and we'll see what this does. Okay. So that did something useful this time, right? We got port count 2, port offset, port stride. Those look reasonable. All right, so I'm going to go ahead and comment this back in, get rid of that, and go for broke, right? Is this going to work? Assuming I can type things correctly. Okay, great. So I will go ahead and do make clean and make. Um, all right. We can now see that this has created two interfaces. Now the question is, do both of these interfaces work? I mean, they're both reporting up, but we haven't done anything to affect that really. So, okay. Go ahead and pull up my notes here. We'll go ahead and add an address, and we will try pinging on each of these ports, right? Go back to ping. All right. Okay, so that port works. All right, so we have an address on this port, which works. We try the other port. We'll do del, and I will add D1. And I need to move the table. Uh-oh. Crap. What happened? Dropping impossible SKB. And it's hung again. Okay. Why would we be getting an impossible SKB? Okay, so this is actually partially a kernel bug. It should not be, let me see, let me take a look at the RX code here. Yeah, okay. This is something that has been reported before. Basically, if the, this is, yeah, so there's a bug in the kernel, and this has caused, I guess, some sort of a shouting match on the Linux kernel development lists, if I recall correctly. Basically, the people that maintain the kernel subsystem are like, hey, this should never happen. If so, it's a driver error. But it turns out that, you know, when you do end up in this particular condition, then there's a kernel bug that causes the kernel to crash. So yeah, that's not so great. So let me think. What do I need to do here? Basically, I can do it. So I need to make sure that this call doesn't get fired off. Or let me pick here. What do I need to do? Git frag on that page. I need to do this differently here. So on map page, that's fine. Maybe because nothing here is related to the page. Null page. Well, null page, there's nothing I can do about that. Okay, so at this point, I've unmapped it at this point. If where's len coming from? Okay. If len is less than fhlen, going to be dropping short frame. Okay, great. And let's see here. Dropping short frame, and then I go to I think that will work. Am I missing anything else here? So if we hit dropping short frame and we go to RX drop, you don't need to do this. Okay, this actually should happen here. Maybe fill page desk. But I've already collected the page here. So there's the page. SKB number frags equals 1. This is doing something with RxInfo, which we don't care about. NAPI GRO frags, we don't care about that. All right, so I think this probably work. So what I think happened here is that because there was nothing plugged in, the RX Mac generated a really short frame, and then the kernel didn't like that, basically. Okay. Booting it back up now. That'll take a minute. And then we'll test this out. The one port works. Let's see if the other port works. And hopefully this this code will be sufficient to prevent that crash. Yeah, actually I should take a look and try to see if I can find that thread on the kernel mailing list talking about that specific bug, because this should not be happening, right? This is where does this happen, right? This is occurring in NAPI GRO frags. Yeah, it's basically a use after free, I think. A use after free or null pointer dereference. Trying to there's a sequencing problem in terms of, you know, it does this dropping impossible SKB, which is fine, but then it does something that it shouldn't do after that, and it's an immediate null pointer dereference. Yeah, that's the kernel bug. It's been there for years. It's been known about for years, but nobody's fixed it because they're like, oh, that never happens unless there's a nick bug. Like, well, all right. This is it's not the way to do development, you know. And the only reason I know about it is because I've been bit by that before. Okay, where was that other? All right, let's try this again. Thing. Oh, shoot. I need to reprogram this. Yeah, I guess another thing, talking about debugging, is I do need to go through the Mac logic that I have and figure out why it's not always padding things correctly. This seems to be potentially a simulation versus synthesis mismatch, because it seems to work fine in simulation, but when Vivado builds it, it doesn't really. So um, I need to dig into that and figure out what's going on there. I have been considering rewriting the padding logic separately for another reason, but yeah, I need to take a look at what it's actually doing right now, because that's kind of an important feature of the hardware. All right, so let's go ahead and try this. Right, let's go ahead and insert the module. Okay, so it's gone ahead and inserted a bunch of stuff, and let's go ahead and add the IP address to the correct interface. Right, we want the D1 version, and hey, there we go. We're pinging. So both interfaces are working. Yes. And I could try a flood ping. Thought I had that. Oh, there we go. That's interesting. I don't know why you would have so much packet loss there. Only 365 transmitted? Oh, we lost the address again? Alright. Something else seems to have broken. Great. But why is ARP not working now? There's the address. So we're seeing the requests come in. Oh, I'm not seeing anything on TX. Okay. Oh boy, what happened? So got packet for TX, got packet for TX. Okay, so it says TX ring full. And then after that, nothing. Okay. That's annoying. Is it actually doing any cleanup on the TX side? Process TX CQ, so this should be doing free TX descriptor at index, whatever. And I'm not seeing that. Interesting. Yeah, this is for some reason not cleaning up anything on the TX side. Okay, so what's going on here? Oh, Right, but hang on, we are getting interrupts. Fill up on RX for both of those. Okay, got packet for TX. Write descriptor index 0. Interrupt. Got packet for TX. I seem to have broken something on the TX completion side, because I'm not seeing, I mean, these interrupts seem to correspond to that. Okay, so we get two interrupts here. This one seems to be related to the process RX completion index 0. Got packet for TX, process RX completion. Why would I not be seeing anything on the TX side? Oh boy, what happened? What did I screw up this time? This is running both the TX and the RX in the IRQ. And we are getting interrupts, which will trigger the transmit processing regardless. So it's not like we aren't getting interrupts, or hang on, are we getting interrupts on this port? Yeah, we are getting interrupts on both ports. Yeah, and we're also processing RX on this port. What the heck? Yeah, so this is the tricky part about this. Is sometimes you end up in a situation where it's not particularly obvious what exactly happened, and you've got a whole. I liken this to sort of a Rube Goldberg machine, where you have a whole bunch of little steps that need to take place in sequence, and if you miss one, then the whole thing kind of breaks down. Let's see, for RX, let me take a look at something here. So for RX, where was this? Process TXCQ for RX. Okay, the RxCQ size. So that one looks correct. And for TXCQ size, that also looks fine. Okay. CQ cons, TXQ cons, TXCQ mask. That should be TXQ mask, but still. All right, let me just try rebuilding the driver again here. Oops, I didn't want to do that. I want to do that. Okay. So now this is firing off free TX descriptor. Okay, that interesting. All right, let me try if I do the flood ping. Does that work? Yeah, okay. Weird. Oh, there we go. 0% packet loss. Okay, then. And I think we lost the IP address again. Yep, okay, there we go. All right, so I don't know exactly what happened and why it suddenly stopped anything on the TX completion path. It's possible that there's some other issue in the hardware that needs to be investigated. It's trying to think of all of the potential explanations for that. One possibility is that there's some problem with the driver and it's not interpreting the, say, the phase tags correctly. Another possibility is that the transmit completion records are not getting written out correctly for some reason. So definitely some need for some debugging going forward. But what are you going to do? Okay, so that's pulled the IP address again. Let me. All right, let's try that first port again and see if it works. So if I do that, and we're pinging again on the first port. So, you know, it's doing something useful, kind of. So yeah, there may be a little bit more cleanup that I need to do here, but I think at this point it's looking just about, I'm not going to say done exactly, but it's looking like it's in a pretty good condition. So there's a handful of things I think that I need to clean up, but I'm going to try to get this. Oh, here's another pointer that I need to put in here. Okay, this should be. Let me see, what other to-dos do I have? Okay, that's fine. Enable interrupts and oh yeah, all right, that's fine. Okay, so yeah, probably some more debugging needs to be done, but it's looking pretty reasonable at this point because we can ping and we can run iperf on both ports. Actually, I guess I haven't tried iperf yet on the second port, have I? Well, we'll try iperf on both ports. So I do iperf iperf 3-s. Bam. Okay, here's one port. We got 1 point something gigabits per second. That's not bad. And then I'll do it on the other port. And that's again about, you know, 1 point something, between 1 and 2 gigabits per second. So, okay, perfect. And then I will try the other two ports. Or the other one port. Alright, so I gotta delete the address here. And then add the address there. And let's go ahead and pull up iperf. Okay, that looks good. Again, 1 point something gigabits per second. That looks pretty reasonable. And the other direction. Yeah, now I guess the next thing that I should probably do, actually maybe this is simple enough to do. Need to look at one thing really quick here. Oops, where did that go? Where was that? Under scripts. Okay. All right. So what I'm going to do now is I'm going to copy a. What am I looking for here? All right. So I'm going to copy this from. All right. I'm copying over a script that will enable changing dynamic debug settings. Well, it doesn't really enable it, it just simplifies it. So this is using either, well, it could be one of two locations depending on the system. So the idea with this is we can enable or disable some of these debug messages. So what we're going to do now is we're going to go through and replace a lot of the messages with a debug version. So let me see here. I think all of this is fine. Mainly what needs to be done is any of the stuff in, so it's like prepare. Okay, that one's fine. At dev info, that should actually be more like warning. No, that's going to be error. All right, and this is going to be netdev dbg, right, for debug. Okay, that looks pretty good. And then again for TX here, we have debug. That's horn dropping short frame, error mapping failed. Okay, TX ring full. This should also be DVD probably. And is there anything else here? All right, so this is going to be DBG. Perfect. Okay, great. So that done. I'm going to go ahead and rsync that. All right, which is the window that I need here? This one. Okay, oops, I don't want that one. Where is the, there it is. Okay. Oh, I also need to remove that. Where was it? That dev debug here. Okay, great. Let's try that. So we're going to see how big of an impact hiding these debug modules or debug prints has on the driver performance. Okay, so we've gone ahead and done the ins mod here. Let me go ahead and we're on the second port, so I'm going to go ahead and add that, and then we'll go ahead and run iperf. Okay, so ping works, but iperf doesn't work? What the heck? Now it's working. Yeah, so that didn't really have much of an impact. All right, so that's, well, I guess it seems to be a little bit faster, right? We're getting up over 2 gigabits per second now. Oh, look at that. We're up at 4 gigabits per second, right? 3.5, something like that. So that's a pretty significant difference just caused by these debug calls. All right, so no argument provided. So what we can do is enable all of the debug statements here. So I can do equals P. Oh, and this shows all of the, yeah, all right. So I can enable everything, and now we can see here's all of the debug statements. And we can rerun that again, right? If I do iperf 3-s and I do this, make sure we have the address assigned here. And look at this, we're only hitting about 1.5 gigabits per second. And if I go turn them all off, so if I turn it off and I run it again, we're up to, whoops, we lost IP. Rapid Network Manager. What are you going to do? Okay. There we go. Now we're up at 3 gigabits per second. So that's quite interesting. And so with that's okay, so that's interesting. So with the reverse path on the transmit, we can hit up to 3 point something gigabits per second. That's not bad. All right, so I think this rounds out most of the stuff that I wanted to accomplish today. I'm considering, so just a couple of words about Corundum Proto, just so we're all on the same page in terms of the point behind this design. There's basically two main things that I'm trying to accomplish with Corundum Proto. One of them is that it's basically a starting point for the iteration of the development of Corundum Micro and Corundum Lite. So Corundum Proto is not really designed for high performance. It's designed to be easy to understand, but also to be kind of a representation of how Corundum Lite and how Corundum Micro are going to be working internally and how they interface with the host. So what I don't want to do is add a bunch of odds and ends to Corundum Proto that make it harder to understand. So I'm probably not going to be adding really much in terms of additional features. However, I am considering adding support for at least TTP timestamping because it does add a couple of additional modules, but it doesn't make the core data path really much more complicated than it is now. Because you basically just have to get the timestamps into the completion records and hand them back to the host. So it doesn't really affect the complexity all that much. Obviously, you need stuff for the actual PTP clock, but the nice thing is that can be kind of segmented out into a couple of separate files, so you don't really need to take a close look at it. I don't know if I'm going to add any sort of offloading capabilities. Like, it would be nice to have like a checksum offload sort of thing, so you can see how that fits in with the core data path, but I don't know. It's probably not a particularly high priority. It's like if I implement some of this stuff for Corundum Micro or for Corundum Lite, then maybe I can see about pulling that back into Corundum Proto. I'm also setting up Corundum Proto as a separate subdirectory, just to make sure that it's pretty separate from the main Corundum Lite and Corundum Micro projects, because it has its own data path, it has its own driver. While it might be nice to share stuff, I guess, in some sense, the whole point with Corundum Micro or with Corundum Proto is to keep stuff separate and to keep stuff simple. So I kind of want to avoid sharing stuff unless there's a really compelling reason to do that. For some of the internal components like FIFOs and Macs, those are shared, but those are pretty generic components. For the more specific data path stuff, I don't think it really makes sense to share it, because again, the idea is to keep Corundum Proto simple and not necessarily optimized, whereas we'll then have the more production grade Corundum Micro and Corundum Lite that are significantly more optimized, either for size or for performance. Um, let's see. Yeah, as I said, I might add a couple of additional features to Corundum Pro, mainly time stamping, yeah, but maybe some other stuff. But I'm not planning on adding very much to it. But the whole point of Corundum Proto is that feel free to download it and mess around with it and see if you can improve the performance. Right? It's a good starting point for building more complex stuff and figuring out how it works and the kinds of things that you can do to optimize that. So that's kind of the idea. Easy to understand, easy to kind of mess around with, but not necessarily something that you want to use as is for anything long term. So yeah, I should also mention the Corundum Proto driver. There's never going to be a FPGA driver for Corundum Proto. If you want to make one yourself, great. And that driver is also never going to be upstreamed because again, it's just an educational thing that's that you can play around with. Oh, that's what I was going to mention. Boards. There's going to be a different set of top-level designs for Corundum versus Corundum Proto. And I'm not going to be porting Corundum Proto to very many boards. If there's a particular board that you want to see it on, let me know and I can add it, but I'm probably just going to support like the Alveo boards and the Alibaba board that I'm currently using. For Corundum Lite and Corundum Micro, the idea is that we'll support everything. Yeah. Well, I don't know necessarily for Corundum Micro, but definitely for Corundum Lite, the idea is to support basically everything. Now, between the two of those, still support everything. I think a good number of designs, it'll probably be like a build option. Do we want to build Lite or do we want to build Micro for this device? But that's not going to be an option for Corundum Proto because that's going to use a separate set of top-level designs. Anyway, I think that rounds out more or less everything that I wanted to discuss for today. And I think I've accomplished everything here, right? We've done a fair amount of cleanup. I need to do some debugging on the we're getting error related to the interrupts. So I got to take a look at that and sort that out, but one step at a time. But yeah, this code here is looking reasonable. I think with a little bit more debugging, I should be able to flesh this out into something that's actually usable. And this, again, it's basically following exactly what the driver is doing, except implemented in Python. So there's nothing particularly crazy here. Yeah, I guess, is there anything else I need to mention along these lines? I think that's about it. Yeah, so hopefully over the next day or two, I want to get Corundum Proto committed, and hopefully also, like it would basically be a copy of Corundum Proto, but an initial revision of Corundum Micro available. Now, obviously, for Corundum Micro, we're talking like this is a pre-alpha effectively, because it's a basis for iteration, and it's going to be probably several months before the driver gets to the driver and the interface gets to a point where this is going to be, somewhat usable. So, I mean, like, it'll work, but that the driver to hardware interface is not going to be stable for some time. And I think once we get to a point where that interface is at least somewhat stable, then we can essentially start cutting version releases. So, but that's probably going to be, I don't know, middle of next year or something like that. Anyway, I think that's about all I have for today, so I will sign off here shortly, and then if anybody wants to continue following along, feel free to hop on the Corundum Zulip. And if you have any other questions, that's the place to ask. And again, if I do more of these live streams, I might not, we'll see, then I'll post the details about that over there. I guess you probably also get notified if you're subscribed on YouTube, but I'm definitely going to be posting announcements on the Zulip channel. So think that about rounds everything out. So thank you very much for tuning in today, and I'll talk to you guys sometime in the near future. Probably next year, right? I mean, it's December 30th, so probably not going to do a stream tomorrow, so talk to you guys next year. Take care.